Well, I've got the CNC control all wired. I've got a big box of cables and motors. Let's hook it up and see it run. Or emit a large cloud of expensive smoke. Either way, it'll be fun. Welcome back to Cloud 42. I'm James. Well, if you've been watching the channel, you know I have been working on a new CNC machine build, and I've been working very hard to cram 100 pounds of electronics into a 50-pound box. Well, the box is now done, so today we're going to take a look at it. We're going to look at the design, the layout, the wiring, and talk about some of the trade-offs and decisions that I made while building it. Then we'll hook up some motors and give it a test run. You think it's going to work? You know it's going to work. Let's do it. Well, this is the box that you saw me build in previous videos. We cut this out with the plasma, mounted the fans, mounted the connector panel, and I now have it all wired and ready to run. So let's take a look at the finished product and understand this is ready to hook up on the machine. I'm sure I will be making tweaks to this over time as I learn new things, pleasant and unpleasant. So what I'm running in here is a Centroid Acorn motion controller. So this is of course made by Centroid, and what you get with the motion controller is just the main motion controller module that connects via Ethernet to a PC, and you get one of these relay output boards. So it's got 8 inputs and then 8 outputs through the relay board. Now I have added additional inputs and outputs by adding this Ether 1616 board. That's the long board that's on the bottom down here. You saw in a previous video when I made the 3D printed mounts. If you look up the video on threaded inserts for 3D printing, that's what I was building, was the mounts for the Acorn board here and for the Ether 1616 and the stacked relays. So the Ether 1616 board down here also connects via Ethernet, and there is a switch mounted underneath the Acorn board that everything plugs into. So it connects via Ethernet, provides an additional 16 isolated inputs, and up to 2 more of these relay boards. Now I'm only running, I've got these all stacked up here, but I'm running one 8-channel relay board that's coming off of the Acorn, and I'm running one off of the Ether 1616 expansion board. Now I do have another connector, and I do have another one of these boards, so if I needed more outputs, I could add another 8, either stacking them up here or find some other place to shove it here in the box. Now the Acorn board has outputs on it, screw terminal outputs down the side that would be suitable for connecting to a stepper or servo controller. I'm not planning on using those. I'm going to use Clearpath integrated servos. So the signal wires need to go all the way to the servo motor itself, and then the servo motor is powered from a separate power supply. And I've got the power supplies right here for the Clearpath servos. And then to actually interface between the Acorn board and the servos, you can wire them all up, but I went ahead and bought a connector board. This is called a C86 ACCP. This comes from a company called CNC for PC, and it's just an add-on board that goes into the screw terminals, has a bunch of pins on the side, connects to the screw terminals, mounts vertically here, and it does a few things if you've got Clearpath motors. One thing that it does is it provides the standard 8-pin Clearpath Molex connectors on the side, so you can just plug your normal Clearpath signal wires right into the side of it, so that's really handy. It also manages the enable and the fault feedback from the servos. So it gets the enable signals from the Acorn, of course, the optical outputs for the enables for the 4 motors, and it processes those, and then it generates its own enable signals that go out to the motors. So that if you enable a motor, here it enables the output, but it is also then monitoring the fault feedback from the servos, so that if one of the servos faults, it can feed that back to the Acorn board and you can deactivate everything. And then of course it takes the drive good signal from the Acorn board that comes up here, and so if anything goes wrong, like an e-stop or any other kind of a shutdown, it will let this connector board know with using the drive OK signal, and it will automatically power down the motors. So this should take care of all of the enable and e-stop and panic functionality. So you panic a servo, unplug it, it should automatically e-stop the machine. You e-stop the machine, it should automatically shut down all of the servos. I was planning on actually making a board to do this, but I got to looking around and discovered it was already available for 50 bucks, and that was just a no-brainer. And so I just ordered one, and so far it looks pretty good. We'll do some testing here a little bit later and see how it works. Let's talk a little bit about the layout and wire routing. Now this is a 20 by 20 inch box, 8 3/4 inches deep. Now that's deeper. Your standard inexpensive boxes tend to be up to about 6 inches deep, and once you say I want one 8 inches deep or more, that's when they really start to get expensive. But I didn't really feel like I had a choice here because of the servo power supplies. These are for the Clearpath motors. These are the IPC5 power supplies, and they're just pretty deep, and especially by the time you put it on a DIN rail and have the connectors coming out the top, I just couldn't find a practical way to fit it into a 6-inch deep box. I could try mounting them on the side, or there's a couple of orientations these are safe to mount in, but every way I came up with, it was just going to sort of wreck the functionality of the box, because if you can't mount it on the DIN rail on the perforated backing plate, then it makes maintenance a lot harder, because you end up having to disassemble things in order to get to other things in the box. So I really wanted to have first order accessibility of everything so that I could get to everything in the box for maintenance without having to take other things out of the way to get to them. Unfortunately, I wasn't able to completely accomplish that. I originally chose this size box when I thought I was just going to be running the Acorn and the servo board. I did not know I was going to be putting in the Ether 1616. I thought I was going to make everything work with the 8 inputs and 8 outputs. I really needed about 9 inputs and 9 outputs to do what I wanted, and Yuchel Kim over at Woods Creek Workshop finally just said, you know you're already making compromises on a new build, you should just buy the board. So I did, I just bought the board. So that made everything a little bit tighter. So as a compromise, I've got the relay boards mounted on top of the Ether 1616, and I have the switch mounted underneath the Acorn board. Now, it's not underneath, right, because this will be vertical, so it's beside the Acorn board. But that means that I can't get to those components without taking something out first. I don't really like that, but it is what it is. I'm not going to get an even bigger box for this. I'm already going to have a hard time finding a place to cram this underneath the machine. Now for cable routing, I really did not want any exposed wires. I wanted everything in wire ducts. If you've never worked with wire duct, this is what the stuff looks like, also sometimes referred to as finger duct, and the top of it just snaps off. Now, all of the fingers have latches, so the top of it just snaps off, and you have these fingers on the side so you can route your wires in, tuck them all in, and then snap the lid back down over the top. And so I wanted to use this everywhere, and unfortunately that makes the need for the box bigger, because, so I've got this little row of components right here, but I had to then allocate space on either side for the wire duct. So it takes up more space, but in the end I think it's worth it because it makes the wiring nice and neat. And as opposed to what I've done in previous boxes, which is put down anchors and use zip ties, you can easily just crack this open and move wires around if you need to, because nothing is actually tied down. It's all just in the boxes with the lids over the top. So let me crack all of these open. Now I of course have no power plugged in, so all of this is cold. But I can kind of show you what I was thinking in terms of cable routing. So obviously we've got these servo cables here on top and the power cables underneath those. But if I pull those up out of the way, you can see how most of this wiring is done. This is just loose individual conductors that are down here laying in the tray. And there's, 40, 50, 60, 100 wires going various places. And they just route through the trays, come out between the fingers, and connect to terminals wherever they're needed. And then, the larger cables are there, and wherever I needed space for something, like I needed something to pass through the side where there wasn't enough space, these fingers can just be broken out. So I've broken out the fingers here at the joint so I can route bundles of cable around corners, but you can see the fingers on these just break out, and they're pre-scored, so you can bend them and snap them at the finger itself. So you can actually just bend it like that and break open at the finger, or you can use a pair of snips and snip it down, and then they're scored at the bottom edge here, so you can break out a whole section all the way down to the bottom, whichever is more convenient for what you're trying to do. Now, one of the things that I really tried to do in here is to keep the high voltage, as in the AC power wiring, separate from the low voltage wiring. It's not always super easy, but a lot of how I laid this out was specifically designed so that I could do that. So the power is coming in right here. So this is the AC power input and output for the accessory outlets, and that all comes and drops down into these ducts here at the bottom. Power input comes around, there is a breaker right here. This is technically a supplemental protector and not a circuit breaker, meaning that it's only rated for disconnecting loads within the box. It's not meant for protecting branch circuits that go out someplace else. Also, with a supplemental protector, it is not rated to trip without incurring damage. So it is allowed to incur damage to itself when it opens in an emergency. They're a lot less expensive, and in a lot of cases they're smaller. So for protecting equipment within a box, a supplemental protector, as I understand it, is fine. You definitely need to understand code and safety regulations wherever you're going to be working if you decide to build something. So the power comes out of the supplemental protector and goes into this contactor. This is a 110 volt AC coil contactor. So I'm tapping off the hot and taking that up to the switch in the front panel, coming back down to the coil. So that's running the coil that then switches the power for everything else in the box. So that switches the power downstream. So this is a 110 volt or 250 volt rated switch, but it's only carrying a small amount of current to switch the contactor, which is then switching the current to all of the power supplies in the box. So the power comes out there and goes down to these sets of terminal blocks, and I've got one for hot, one for neutral, and a block of these for the earth ground. And these are just DIN rail terminals that are bussed together. So that's just the main power distribution to go to all the power supplies. So AC comes to the bottom side of these three Meanwell power supplies, and this relay, so the AC comes over this far, servicing the bottom of this, and then some of the AC wiring comes over this far in this duct here on the top to power these two power supplies up here. And so all of the AC power then is confined to this corner of the box. Nothing goes beyond this point here, and nothing goes beyond this point here on the bottom. So everything over here is low power DC. Now I do have a few places where the DC wiring that comes up here comes by the AC wiring right here, and they share maybe an inch of this duct, but this is the earth ground, and these are the earth ground lines, so it's not actually sitting next to the hot. The next one's over neutral, and then the hot wires are further on down. So I've separated it as much as I really can in a box this size. Then from here over, we've got the power coming out, being distributed out to the Acorn board here, up to the interface board here, and over to the Ether 1616 here. And then of course there's power going out to the relays and to the inputs, and we'll talk about that in a minute. And then further on over here, I do have some distribution for the DC power, so places where I had to make multiple connections and there weren't enough terminals on the power supplies. So I've got an auxiliary ground, a 5 volt ground, and a 5 volt distribution block. And then as far as low voltage signal wiring, that is almost all routed just up this main channel in the middle here. Everything is set up so that all of the outputs for the servos and some of the inputs on the Acorn board come out this side. The Ether 1616 inputs come out here. The relays for both the Acorn and the Ether 1616 come out here, and it all just goes into this wire duct. There are a few wires that come out this side, go into the duct in the top, and then just route down. And so that provides me with one raceway to get everything right down to the panel here. So it comes down and then comes out and up to the connectors here, to the terminal blocks on the PC board that I showed last week, and then the servo connections here. The only thing that's not low voltage power in here is this. These are the 72 volt DC power cables from the servo power supplies that go down to the servos. I don't actually anticipate this being an issue. It would have been nice to instead route that stuff around this side of the box, and I still could, but there's no room for the wire ducts, so I went ahead and ran it down through here. Again, it's DC. There will be some current spikes because of the way the servos work, but I honestly don't think it's going to be a big deal because all of the signal wires going to the servos and the switches coming back are all opto-isolated circuits, so they're all running. They don't have a common ground, and they're all running with a relatively large amount of current, maybe 5 to 20 milliamps at 24 volts. So I don't expect them to pick up enough noise to matter. If it ends up being a problem, I can just route these cables down this side of the box, even though I don't really want to. Let's talk briefly about power domains. Obviously, you've got a lot of stuff going on in here, right? We've got motors, we've got a bunch of relay switches here, we've got a large relay for running the dust collection system, we've got 5-volt fans, we've got a network switch under here, we've got solenoids, and then also powering things outside the box, we're going to have a servo brake. There's a bunch of different stuff going on in here, and we want to keep the power domains separate to prevent noise from the higher power systems from affecting the logic. And so I decided to separate this into 3 separate domains, and I've got 3 separate Meanwell power supplies here to provide that. Now that, of course, is separate from the servo power. The 72 volt servo power is being provided by these supplies from Teknik, the IPC5s that are intended specifically for the Clearpath servos. Those are completely independent. The outputs are floating. The way they run these systems, the negative side is not connected to earth ground. The 72 volt power is completely floating. In fact, the only DC power in here that is referenced to earth ground is this, and that is the logic, the 24 volt power supply for all the logic systems. So this will supply the Acorn board and the Ether 1616 board, which then of course provides the power to run the relays. But I'm not using this 24 volt supply for any switched power on the side here. So to run a relay here, to run the pneumatic valves, to run the servo brake, anything that requires current, I've got a separate power supply for that, especially because they're inductive loads, and I don't want the spikes from that stuff switching on and off getting back into the logic. So this first power supply, this is a 60 watt, 24 volt supply, and that's supplying the Ether 1616 board, the Acorn, the Clearpath interface board, and then any of the sensors. So this is also providing, this is what I'm calling the 24 volt logic bus. And so this is providing the 24 volts for all of the inputs that are then opposed to the switches or the proximity sensors that then pull it down. This also powers the proximity sensors and any of the sensor inputs that are run through this PC board. And that's all that this powers. The second 24 volt power supply, and this one is 24 volts, 1 amp, so this is what, 25 watts? This 25 watt supply, also 24 volts DC, is not connected to earth ground. It's floating, and it provides power for these switched outputs. And these switched outputs run things like the servo brake and these pneumatic valves and this relay for the dust collection system. So that's used only for the switched power. It's isolated because these are just dry contact relays that are running it. And so this is an isolated system. It can be as noisy as it wants. Of course, I do have diodes, flyback diodes on all the coils and on the brake to absorb the inductive kickback so that it doesn't destroy the relays. But this is a separate power supply so that the noise doesn't get into the logic. And then I was planning on having a third power supply to run the fans in the box, 12 volt, just because 24 volt PC case fans are hard to come by. But I ultimately switched to 5 volts. And the reason is because the network switch that's under here requires a 5 volt power supply. And I can't find it right now, but it of course came with a little wall wart, and I did not want to try to figure out how to put that in here. So I'm running that network switch off of this 5-volt power supply, and this 5-volt power supply is also then running all of the fans in the case. The one here, and then there are two 40mm fans, one each on the top of the servo power supplies down here. So when you switch things on, all the power supplies come on, including the 5-volt that runs the fans and everything else, and the switch here in the box. Let's talk briefly about inductive kickback. So anything that has a coil in it is going to produce a negative voltage spike when it switches off. So all of these relays do that, but there are diodes on the board to protect the circuitry from that and absorb that. For the pneumatic valves to run the air purge for the spindle, the automatic tool changer is air activated, and air blow or mist coolant. These valves, I actually installed diodes right on the terminals, reverse bias, so they will absorb that. This relay actually has it built in, and then I installed a diode on the brake as well, and then this contactor has a little modular absorber system in it. So there's a little slot here on the top, there's an empty hole, and you can buy these little modules depending on what kind of coil it is, whether it's AC or DC, and you can buy these little snubbers that are appropriate for different applications. So I've got one here that's appropriate for the AC voltage that I'm running. These just snap in, and it's just a little snubber that goes across it, so you don't have to worry about diodes or external capacitors or snubber circuits or anything. These are just little optional parts that you buy, whichever one is applicable, and drop it into the contactor. I thought that was pretty cool. I think that is all we've got going here inside the box. Let me button this back up. This is the computer that I'm planning to run. This is a little B-Link mini PC. Now, if you go to the Centroid website and look at their specs, they have very, very stringent specifications for what you're allowed to use or what they recommend using with the Acorn controller. And it's a surprisingly beefy machine that is required. It doesn't require a lot of memory, but it requires a CPU with a pretty stout single core performance. And that's just to make sure that the machine can actually keep up when you're cutting, and so you don't fall behind and end up underrunning the buffers. And it's a pretty stout machine, but I opted to actually go a little higher end than what they require. Now, what they recommend is an Intel NUC, and they have one you can buy pre-configured. They also have a touchscreen machine you can buy pre-configured. They are relatively expensive compared to what I could build myself or what I could get, so I'd opted to go with this. Now, this is a quad-core 8th gen Intel board that actually, in terms of specs, it's got about double the single core speed that is required for the Acorn, and then of course it's a quad-core processor. I think they only require about 4 gigs of RAM. This one's got 16, and the reason that I over-spec'd it so much is because I want to be able to run other stuff on the machine. And yes, I know running other things on your CNC controller machine is a bad idea and is not recommended. However, I'm running a YouTube channel here, so I'm going to want to run screen capture software on the machine so I can capture the screen when I'm running CNC operations, among other things. I'd like to be able to crack open my CAD package and make a quick adjustment. I'd like to be able to bring up and look at documentation. This machine should have more than enough power for that. And if I end up with a problem where I'm running extra stuff on the machine and it's causing problems with the cutting, then I just won't do that anymore. Now, key things on this machine, I've got plenty of USB ports. It's got HDMI out, so I can run an HDMI. I'm actually going to run a little portable HDMI touchscreen. So this is just this is a portable monitor. It's got fingerprints all over it, of course, but this is just a little portable monitor that's designed to take as a portable second screen for a laptop. But this is a touch screen. It connects with mini HDMI and USB-C, and it actually gets its power from the computer. So that's all I have to do is run a USB cable and HDMI to it, and I've got a touchscreen monitor. This has a LAN connector so that I can connect directly to the switch in the box. And then it also has Wi-Fi on board so that I can connect to the Wi-Fi network here in the shop, both to transfer files into it, but also to have a handy web browser here in the shop when I need it. Now, the one other device I plan to connect to this PC is an MPG, stands for Manual Pulse Generator. This is the one that is provided by Centroid, well, provided in exchange for legal tender. And this is RF, there's no cable, and it actually has a separate center-loaded antenna that's used for this. So it's not Bluetooth. Well, if it is, I'm impressed. But it's got a long-range antenna, and I've been pretty impressed with the range of this thing. I can walk all the way to the other end of the shop, shadow it with my body, and it still works. In fact, I can take it into my office at the other end of the house, and it will still connect. And so this just has a little USB receiver with a little coaxial connector, and that just snaps right in to a USB port, and you are good to go. Of course, the computer's not on, so it can't connect right now. And this particular one just connects up with the CNC 12 software and the Centroid controller, and everything just works great. We will power this up in a minute. Let me get some motors. Let's plug this all in and see if we can make it work. These are the motors I'm going to use. These are NEMA 34 motors. In fact, these are some of the biggest NEMA 34 servos that Clearpath makes. So these are the big boys, and they're wired for extra torque and to run slow. So these particular ones are configured max speed of like 1130 RPM, but just monstrous amount of torque. It should be more than enough for the build that I'm doing. And in fact, these should be sufficient for a much beefier machine if at some point I want to transplant the brains into other hardware in the future. Now, the Clearpath servos just have the 72 volt power and the 8-pin connections here, and I've got a bunch of cables ready to go. So let's connect all of this up. Okay, 4 axes here, X, Y, Z, and A, and in this case, since this is a gantry with a dual Y drive, the Y motor and the A motor are going to be slaved, and those are going to run the 2 ends of the same axis. Now for the Z, of course, because I've got a servo driving a ball screw Z axis, when the servo is powered off, the axis could drop, so we have a brake. And this is just an electromagnetic brake that will attach to the front of the servo so that it can apply braking force when the power is off or when the servo is deactivated. But for now, I'm just going to set it over here. I'll plug that in. Got the network cable coming from the PC. Plug that in. Most of these connectors are for, the first 6 here are for the limit switches and the homing switches, which of course I don't have a machine with switches on it yet, and for the probe and for the tool touch off, which again I don't have, but I can connect the e-stop and the button for the tool release. So I just have an e-stop, normally closed switch here set up that I can plug in. And then I also just rigged up a switch that I can use to simulate the tool release. This will be a foot pedal eventually on the machine. And then the last thing I want to do is I want to hook up some air to the air fittings just so that we can see those operate. I've got an air line here. And then I'm just going to stick some little pieces of tubing in the outputs, just to make sure we don't blow out an O-ring or something funny. So I got power for the box here, and then I'm going to put some power in here for the dust collector accessory outlet, and I'm going to plug a shop vac into the accessory outlet up here for the dust collection. You won't be able to see it, but trust me, you'll be able to hear it. Okay, let me get a screen capture running on the computer, and let's power this thing up and see how it works. Okay, I'm going to power this up. So that powers on all the equipment in the box. You saw the servos just lurch to life, but of course they're not powered right now. They're just they're powered on, but I can see the lights on the back. They are not active. And the brake is locked. It will not turn. Okay, let's start the CNC 12 software. Now I'm going to use a mouse here just so you can see where I'm pointing, but in actual operation I'll be using the touch screen. So this is connecting over the Ethernet, finding the Acorn and the Ether 1616 board, and it comes up in a reset mode. I will click here the reset switch, and now everything is online. I will hit cycle start to do the homing cycle. It's all set up manual right now because there's no homing switches, and that should activate the motors. And sure enough, the motors are active and the brake is now free. So because the Z motor has activated, this is free. If I hit the E-stop, that's now locked up and the motors can be freely turned because they're deactivated. Turn that off and then reset the motors. This is locked, reset the motors, and there we go. It's all free and everything's active again. Let's power up the MPG. Okay, so that has connected, and you probably can't read that, but I can see the DRO displays, the same as what's here. Let's select X-axis, and we can turn the motor. Slow or fast, that's X. Y, you can see the two axes are slaved together. Z, nice and simple. Now I've got this positioned right now all the way over here at around 24 and 24 inches, which is near the machine zero coordinates. Let's go ahead and do a little test here. Let's run the Z axis down a ways negative. So let's run this down about 7 inches negative. And so we're sitting at 24 inches, X and Y around 24 inches. And Z is negative about 8 inches. Let me just hit the button here to go to work coordinate system XY0, and what we should expect is that it should raise the Z-axis up to the top and then traverse all the way back to 0. And this thing should run pretty fast. There it goes up and traversing back to 0. And I don't know if you noticed up here is the feed rate displayed. I'll go back to where it was, which is where the machine zero. You can watch the feed rate that it's running at. 566 inches per minute. That's about 14 meters per minute, 14,000 millimeters per minute. That is fast. And that's about the fastest I can run with these with the 10 millimeter pitch ball screws that are going to be in the machine. That's these things running up around 1300 RPM, 400 inches per minute per axis, but when you're going diagonally, multiply that by the square root of 2 and you get 566. Okay, that's the motors. Now let me go over here into the utility and I can show you what I've got configured. Utility, click here for Acorn Wizard, we'll bring up the wizard. Now, this is really pretty simple. So under axis drive type, I just came in and selected Clearpath. And so then that sets up some things like the steps per revolution, 6400. I did have to go configure that in the motors using a USB cable. These are the enhanced version of the servos that have the higher resolution. The non-enhanced versions are limited to 800 steps per rev. These ones are running at 6400, up to 2200 kilohertz, which is well in excess of the speeds that I need to run here. And then for input definitions, the way the Centroid system works is you just grab predefined behaviors and drag them over. So for input number 5, which is what I have coming from the Clearpath board, I just drug over the drive OK behavior, so it knows if the Clearpath motor is active, and if it has a fault, and then it feeds that back through this drive OK signal. And then I have the E-stop on another input over here, and then this tool unclamp button I have configured on input 6 on the Ether 1616. Then for outputs, I have some VFD outputs enabled here, which I don't have the VFD hooked up yet. I have the no fault out on output 8. That's what goes to the Clearpath interface board, so that if you E-stop, that's what causes it to deactivate the motors. And then I've got on some of these other outlets the Axis 3 brake release. That's this Servo Brake. I've got an air blow nozzle, unclamp tool, which is for the automatic tool changer, and spindle cooling fan, which comes on when the spindle is running, so it'll deliver air purge. And then I got router dust collection set up, which again runs the router dust collection switch here. So those are all set up. Let's give them all a try. Let's just start by powering up the spindle, and we should get air in the air purge. Of course, there's no spindle to power up. Put that in manual mode. And we get air from there. Let me switch on the air blow. And we get air from that one. And then the other one is the automatic tool changer. So I've got the tool unclamp button here. And we get air from that. So that's working. Let me turn on the dust collector, which should power up this accessory outlet, which has a shop vac plugged in. And that works. See, is there anything else here? Oh yeah, I wanted to test the servo panic. So let's unplug the Z motor. So the Z motor is plugged in. Let's say we had a problem with this and it panicked, we over torqued it, or it just lost its connection. You would expect the whole system to go into E-stop, or at least shut down the drive. You want to shut down the other drives as well, right? If you're actually running a program, you don't want, and you suddenly lose the Z motor, you don't want it to continue. So let me just unplug this. And that is now dead. And the brake is now clamped. And the other motors I can see are all deactivated. And over here on the computer it says drive fault. So it detected that, shut everything down. Plug that back in. And let's do a reset cycle. And there we are. We're back alive. Motors are locked. Brakes released. So all of that's working. Well, that is about as far as I think we can go without actually having a machine to mount all this stuff on. And that's what we're going to work on next time. If you enjoyed this video, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.